Good morning, everyone. So one quick thing to mention before we get started here, we're going to pick up from the end of Chapter 5, Section 5.8. We had left a section off of Chapter 5 for reasons I'm still trying to figure out. But we did leave a section off. In a way, it's a good section to leave off because you'll see that it involves a delta, like a lot of delta H's, that ends up being reactants minus products. So it's one that stands out as being a little bit of a different way of calculating it from some of the other delta H's in Chapter 5. But the other thing I want to make sure that I mention up front, so you guys are aware, our next midterm's in 2 weeks. So we're going to have a fast turnaround for midterm 3. Midterm 3 is only going to be this last section from Chapter 5, Chapter 6, and then Chapter 7 we only cover like half of it anyway. So we're only going to cover the first 4 sections out of Chapter 7. It's a pretty quick chapter. It'll take probably no more than a lecture or so to cover the topics in Chapter 7. And once we kind of get through the first half of Chapter 6, we're going to kind of get rid of the math for a little while, or at least we're going to get rid of a lot of the sort of more gory math problems and kind of get back into some concepts. So we'll at least get rid of the calculator for like half the test. One good thing to think about is this section here that we're going to cover, hopefully very easy, a very easy problem that we can solve here with the end of Chapter 5. And then when we get into Chapter 6, there's a couple math problems hopefully we can get through, and then some concepts that we can understand. So I hope we have a couple easy, not easy, I don't want to say that in a way to suggest that we should get like glowing scores on midterm 3, but we have a chance on midterm 3 of having just a small set of material that hopefully we can learn to a good level and use that to get hopefully a higher exam average to help pull exams up. And another thing to think about exam scores too versus the rest of the class, I was just looking at the homework average. It's like 85% for the class. I was looking at the recitation average. It should be 100, but it's like 98%. And so that's pretty good. And then the lab average is like running at 92, I think, right now. So I mean, the 40% of our class runs at an average in the 90% plus range. It has the opportunity for you guys to earn scores in the 90+% range relatively easily. So it's just that 60% of the class that we kind of have to worry about in terms of exam scores. So it is possible to make up from exam scores that aren't where you want your final grade to be. So we'll think about that as we go along. I'll have probably a few more words about scores on midterm 2 once they're collectively in. But so far it's looking like the average is not so different from midterm 1, which if you recall my words after midterm 1 was that midterm 2 is going to be a lot harder. So far scores looking pretty good. Not dropping off like I had feared they could. So I think that's a good testament to you guys studying. So I'll have a few more words about midterm 2 probably on Friday once we get some more of the scores in. Of course, you guys don't know anything yet either. So I think by Friday, I think you guys will see your score. So I'll say a few more things later. Okay, so let's get into section 5.8 here on bond enthalpies. So that's what the section's about, is sort of quantifying or looking at different strengths of bonds. What these energies correspond to is the energy it takes to break the bond. So when you see a bond enthalpy, like let's look at F2, for example, we could look at any of these examples here, but this bond strength would be that bond turning into 2 fluorine atoms. And so breaking the bond takes energy, takes 155 kJs per mole. If you want to break, let's say a hydrogen-hydrogen bond, so that's here. So if you want to break the H2 bond, it's about 36 kJs per mole, so a stronger bond than F2. We're not going to try to decipher why one bond is stronger or weaker than another, but you can see that depending on the atoms in the bond, you have a different bond strength. And so the H2 bond would correspond to the energy it takes to break the H2 bond into 2 hydrogen atoms. You could break the CH bond into the carbon plus hydrogen fragments or the carbon plus hydrogen atoms. So notice that every bond enthalpy on this chart is positive. So the bond enthalpy is always going to be positive because energy has to be absorbed by the bond to break it into its fragments. So in other words, bonds are stable. You have to add energy to break the bond into its fragments. And then when we make bonds, if you imagine having the opposite reaction, if you imagine taking 2 hydrogens, trying to turn them into H2, now this reaction here should be exothermic. So making bonds from atoms should be exothermic. Breaking bonds is endothermic. And so all these enthalpies here that we're describing for breaking the bonds are endothermic. So you can also then say the greater the bond enthalpy is, the stronger the bond. We won't chemically get into why one bond is stronger than another. So we're not going to really say, well, why is the H2 bond stronger than the F2 bond? that's really not a topic for this class. The topic for this class is just kind of noting that they have different bond enthalpies, that they're both positive, and then we'll see that we can use bond enthalpies to help us approximate or get a picture of what a delta H of a reaction should look like. So also wanted to point out here, this last bullet point here, energy is always going to be released when a bond forms from its gaseous fragments. A little hidden detail in this chart is that this is kind of assuming that all these substances are in the gas phase in terms of calculation. Then when we go to do calculations, you could have a variety of phases. So when we're going to try to calculate a delta H here, it's always going to be an approximation. So we can approximate the delta H of a reaction by the sum of all the broken bonds that have to be broken in the reactants, and we're going to sum the enthalpies of the bonds that are formed in the products. So if you notice that this might seem strange, that this is a delta where we're taking the reactants sum minus the product sum, but we'll see on the next slide, or next couple slides, that this is a consequence of how Hess's law is working here. So what we're going to try to quantify is for a given reaction, how much heat has to be absorbed to break all the bonds. That's going to be endothermic. And then how much heat do we release when we make all the new bonds? And so then when we start thinking of a given chemical reaction where we're taking a collection of bonds and turning them into new bonds, you could think of H2 plus O2. So you could think of this reaction perhaps that we know is exothermic because we've seen it with our eyes, this reaction here. So if you're picturing this reaction here and kind of saying, well, why is it exothermic? We know, we've seen this reaction take place with an explosion. We know delta H is exothermic. We could look it up. We could look up enthalpies of formation. We could look up, like we could do a bomb calorimetry experiment, get the delta H as well. There's other ways we can know the delta H, but we can approximate it here in this section. And when we do so, we can kind of get a picture that the reason this reaction is exothermic is because when I break all of these bonds, that it's going to take less energy to break those bonds than the energy I get back when I make the new bonds in water. So if we sort of picture this reaction here as having to break 2 moles of the H2 bond, we have to break 1 mole of the O2 double bond. So we have to break these bonds here. And so if we're sort of quantifying how much that's going to take, the H2 bonds is 436 kJs per mole. We have to break 2 moles of the bond. So there's 2 moles of H2 in the reaction, so we're breaking 2 moles of that bond. So we have to have 436 kJs per mole times 2 absorbed to break those 2 bonds. And then we also have to have the O2 bond broken, which is 495 kJs per mole is the oxygen-oxygen double bond. So we have just 1 mole of that bond. So I'm going to add 495. So in order to convert all these atoms here, or all these molecules here, into their atom fragments of 4 H's and 2 oxygen atoms, collectively that's going to take 1367 kJs per mole of energy being absorbed. So I'm starting from my starting point, my H2, my O2. To break those bonds takes that much energy, so I have to have these reactants absorb that much energy. Then we're going to get back energy when we make our new bonds. The energy we're going to get back is the energy in our 4 bonds in water. So water, of course, has this structure. This topic here, we don't know Lewis structures yet. You probably know the structure of water from past examples. If you need to know a Lewis structure to solve a problem here in section 5.8, we'll show you a Lewis structure. So you'll see some practice like quiz problems on this topic, some homework problems. Usually will show you a Lewis structure so you know what type of bonds are involved. But we have 2 moles of water. So I'm forming here 4 moles of the OH bond, which is right here, 463 kJs per mole. So if I go 4 times 463, so this bond here, 463 kJs per mole, I have 4 moles of that bond that's forming. That's equal to 1852, but we're making these bonds, and that's exothermic. So I'm taking the atoms and forming the bonds, so that's why that becomes minus 1852. That's how much energy we go downhill. So hoping you can see is a really simple like sort of result you get from a problem like this is you kind of see that an exothermic reaction is exothermic because we're making stronger bonds. So exothermic reactions make stronger bonds. If we have a reaction that happened to be endothermic, then we're making weaker bonds. You could easily flip this chemical reaction right and picture that that's going to be an endothermic reaction. If you had water convert back into its elements, that's endothermic because the bonds in water and the reactants then are stronger than the bonds in the new products if you flip the reaction. So here we're seeing that the product bonds in this reaction are collectively stronger than the reactant bonds. So I hope this topic helps us understand that the reason why a reaction would be exothermic is we're forming stronger bonds, we're forming more stable bonds. We're starting with less stable bonds or weaker bonds in the reactants. And we can see this play out with other examples too. So let's take a look at a second example. And this will be another combustion reaction. So here we're combusting CH4 instead of H2. So we have CH4 combusting with the O2s, forming CO2 and water. And the question is, can we approximate delta H here for this reaction? We know it should be exothermic just by the nature of this reaction being a combustion reaction. So we should know it should be exothermic. And then what we'd want to know is, well, what are all the bond enthalpies here? And how many of the bonds are we breaking? So we got to break 4 moles of the CH bond. That was 413 on the previous slide. 495 kJs per mole for the O2s. And so we can quantify how much energy it takes to break those bonds in their atom fragments. And so to go to carbon plus 4 hydrogens plus 4 oxygens takes 413 kJs per mole times 4, takes 495 kJs per mole times 2. So collectively, we have to have this reaction absorb plus 2642 kJs per mole if it were to break all of its bonds. Let me take a side step to say that this isn't how the reaction takes place, that this isn't how we're implying this reaction occurs. This is just a way to calculate a scheme to approximate the delta H's. We're just saying if all the bonds were to break, the molecules would have to absorb 2642 kilojoules of energy, and then we're going to get back the energy for the CO double bond and then the OH single bond. And so the CO double bond strength on the chart, if we looked it up on that previous slide, was 799 kJs per mole. So we're making 2 of that bond, so that's why we have this times 2. And then we have 4 moles of that 463 kJ per mole OH bond. And so that gives back minus 3450 kilojoules per mole when we have these atom fragments turn into the new set of bonds. And so if you think of bond enthalpies being endothermic, we've just flipped that reaction to the bond formation being exothermic. So we're taking the atom fragments, turning them back into bonds, and then we're getting back energy here. So you can see that it's the sum of the reactants minus the product, just really as a consequence of Hess's law. So just a consequence of Hess's law that we can add up these 2 delta H's by summing up the reactants bond strengths minus the products bond strengths. So we do the final addition here, 2642 minus 3450, just adding up reactions, add up the delta H's. So we're just adding our delta H's here, and then we come up with minus 808 kJs as our predicted approximate delta H here. Now that's the only weird part about this section is that this gives us approximate values because we're using average bond enthalpies for a bond that will vary slightly with different compounds. Like a CH bond is about 413 kJs per mole, but not every CH bond is exactly 413 kJs per mole. So that's another reason why we're getting approximate values here. So know that this is an approximation technique, not a direct calculation of a delta H, but it's a way to understand just why a reaction like this is exothermic is that the collective products bonds are stronger bonds in the products than we have in this example here than in the reactants where the reactants bonds are weaker, take less energy to break. And so then this one kind of basic question that I have here in the notes that kind of takes us back to that hydrogen gas, oxygen gas. So just think when we give a spark to that mixture, we saw the balloon explode, we saw that combustion reaction taking place, that was all the heat that was being given off from that reaction. So which statement seems to be the most true? You can just think about this one on your own. We won't worry about doing this online or anything. So just take a minute or two, read through the choices, and think about which one most applies. All right, so we'll take a look at the answer. So the reaction doesn't absorb energy. This reaction is giving energy off. And so we see the energy, the heat given off from this reaction. And then, so the reaction gives off energy because the product's bonds are more stable. Answer A. So then stability or strength, we're kind of thinking of this in terms of like an enthalpy diagram where enthalpy is highest at the top. So this would be our 2H2 and our O2. This would be our 2 water. The more downhill on this chart you are, the more stable you are. So that's why we'd say that that water here is more stable. And then the collective bonds of water to make our atom fragments is stronger. So to go from water to atoms, more energy than our reactants take to go to those atom fragments. So the energy it takes to break all the bonds in the products, more energy. The energy it takes to break all the bonds in the reactants, less energy. So the products bonds are stronger. So more stable, stronger as well, we can say, for this reaction. And if we had an endothermic reaction, we'd just be flipping the logic. So if we had an endothermic reaction, we'd just be flipping the logic that the products bonds would have to collectively be weaker than those in the reactants. Okay, so there is one more section in chapter 5 that we were intending to skip all along. That's the foods and fuels section. So the very last section of chapter 9 is one that we skip on foods and fuels. So you can not worry about focusing on that section as we now kind of detour into chapter 6. So as we start chapter 6, though, we kind of start a new sort of unit, if you will, where we kind of start to go from trying to understand properties of the electron, which we're going to see start with trying to understand properties of light in chapter 6. So we're going to see how there's sort of a wave property duality of light. Then we're going to see the electron has a wave particle duality as well to help us understand what the electrons are doing in atoms. We're going to then cap the chapter off with trying to understand electron configurations. I feel like that's something that most students tend to remember from high school. Like if I just said, do you remember the electron configuration as something like carbon? Do you remember doing these things where carbon would be like a 1s2, a 2s2, a 2p2? If you remember kind of something about that, that's where we're going to end the chapter with, is trying to go through most of the elements on the periodic table and understand what their electron configurations are. So eventually that's what we're leading to here in chapter 6. And so we're going to just start off with understanding light, try to see how that helps us understand some properties of the electron. As we get into chapter 7 later, it's going to describe properties of the nucleus, so it's going to describe sort of the left to right trends. That's another thing I think most students remember learning. They always forget the trends though, and I would expect that you probably don't remember ionization energy trends or atomic radius trends, but you probably remember there being left to right trends on the periodic table. That's what we talk about in chapter 7. And so then when we get into chapters 8 and 9 after midterm 3, that's where we start getting into bonding, Lewis structures, three-dimensional shapes. And so again, you might remember sketching Lewis structures, maybe you forget how, and so that'll be our topics for after midterm 3. Okay, so let's get into sort of describing light. So for describing light, we tend to describe it with either the wavelength or the frequency of the light. So the wavelength is how long light travels between wave cycles being completed, and then the frequency is how many number of waves pass through a given sort of unit of space per unit time. So frequency is like how many of these cycles are completing in a certain amount of time. And the product of the wavelength and the frequency is equal to the speed of light. So the speed of light c is equal to the wavelength, which is just how long in space it takes one cycle of the wave to complete. So this is a distance in unit of length, like a meter or a centimeter, so some distance of length. And then the unit of frequency is, if we imagine that this is, say, 1 second of time here, how many of the wavelength cycles are completing between this interval here? Then we would say there's 1, 2, 3 cycles completing, so that would be a frequency of 3 cycles per second. We'd call that 3 hertz, where a hertz is an inverse second, or it's a cycle per second. So we use the unit inverse seconds a lot for frequency. And so if you think of frequency here, having the units of inverse seconds, you have length times inverse seconds gives you the speed of light c. The speed of light, most students just always use 3 times 10 to the 10. Usually I use 2.9 2.9979 times 10 to the 8 if I want to be slightly more precise, or 2.998. But you'll see this number a lot here being used in this chapter for the calculation of a wavelength or a frequency given the other. And then also this is the speed of light in a vacuum. So if you have light permeating through different media, it could have a different value. But in this chapter, we're always imagining light propagating through a vacuum. So this is the units that we use for the speed of light. We then also could talk about the electromagnetic spectrum. So the spectral range of light from the radio frequency, which is described as having a long wavelength. So the long wavelength sides are radio frequency. The short wavelength sides are gamma ray or X-ray side. So the gamma rays and X-rays have a very low wavelength or very short wavelength. And then if you think of light of all forms travels at the same speed, so if light of a long wavelength, so imagine light has a long wavelength, then the frequency has to be small. There's going to be a few number of cycles completed per second. So we have a low frequency or a low nu value. The Greek letter N is the symbol nu here for the frequency. And so we have a low frequency on the radio frequency side, and then on the gamma ray side, we have a high frequency. So you can see the frequency varies from about 10 to the 4 to 10 to the 20. 10 to the 20 is obviously a higher frequency. So we have a lot of cycles per second being completed in the gamma ray side. And so now if you start to think about the relative energies of the different sides of the electromagnetic spectrum, are you going to be more afraid of the long wavelength or the short? Probably the short. So the gamma ray is the high energy side. So this is the high energy side of the electromagnetic spectrum, and this is the low energy side. So it's going to be more probably it'd probably be a better idea to have radio frequencies bouncing around the room ad nauseum compared to gamma rays. So might do a little bit more damage if you have the high energy photons passing through a given room. So we have our high energy side or low energy side, and so gamma rays to X-rays to the UV to the visible kind of take us through the really high end to the sort of reasonably high energy side. So sunlight is carrying wavelengths in the UV to the high energy side of the visible spectrum. This is the light that you can get sunburned by. So you can think of that being relatively high energy. And as you go to the opposite end of the visible, the blue-violet's the high energy side of the visible spectrum. The low energy side's the red-orange side. As you go to the lower energy side of the visible spectrum, that carries a lower energy. And then that takes us into the even lower energy side of infrared, microwaves, and into the radio frequency. I don't think you need to know too many cutoffs for where we're cutting off these different ranges, as opposed to just knowing gamma rays, X-rays, UV to visible. That's our higher energy side of the spectrum in that order. And then on our lower energy side, you have the infrared, microwave, radio frequency part of the spectrum. And so the specific cutoffs aren't too important, other than about 400 to 750 nanometers. We'll use those a fair bit. So just kind of knowing that's the range of the visible spectrum. I used to think it was strange that the visible spectrum is so small compared to all of the wavelengths of light. So why might it be that this visible spectrum is where it is? Well, if you go back to the bond enthalpy chart, and something we'll get to maybe in a couple slides, is kind of thinking of how energy can be used to break bonds. And to break a bond that's about 400 kJs per mole is going to take right around an energy in that region, or a photon in that region there. And so I think it's really good for us to be able to see light that's like just sort of at the threshold of energy that's going to start to cause negative reactions to happen with us. Like bright sunlight, we know to look away from it. Why? Because it burns. Why does it burn? It burns because it's breaking the bonds in the compounds in your body. And so I think it's really good for us to be able to see light so we can sense the light that we want to move away from. And I'm sure that's evolutionary-wise why this is the range that we can see, because it's sort of telling us in the blue-violet side, that's the danger level. So the energies on kind of this side here are the energies that are going to carry enough energy to start breaking to sort of molecules in your DNA, can lead to skin cancers and all those negative outcomes. So I think it's good that our threshold of seeing is right in that region there. Kind of for the same reason why feeling freezing temperatures is always a good thing, because you want to know when you're about to get frostbite. It wouldn't be helpful to change where you feel temperature, because the next thing you know, your hand's frozen and you never knew it. So I think there's a good reason for the visible region where it's at. Okay, so just a few calculations we might do are going from, say, a wavelength in a certain unit to calculating like a frequency in some other unit. So the hertz is an inverse second. What we have to use here is the speed of light is equal to lambda times nu. If we want to calculate the frequency, we're going to have to take the speed of light, divide it by the wavelength. We're going to have to account for units. That's the one thing, well, many times I'll say this, but if you ever make a mistake in a problem and you didn't show units, probably it's because some units weren't canceling out, and we need to think about what units we want to plug things into. And so if we use the units on the previous slide for the speed of light, 2.9979 times 10 to the 8 meters per second, I'm going to want to divide by the wavelength, but in units of meters. So I can start with 725 nanometers, but I just want to convert this over to the meter unit so that it can cancel into the units in the speed of light. And so this is kind of gets us back into our prefixes here. So we haven't used the metric prefixes in a while other than like milligrams or kilograms. And so micro is 10 to the minus 6, nanos 10 to the minus 9, and then pico is 10 to the minus 12. And so I think you'll probably see that nano is the one that we're going to use the most in this chapter. So we're going to use nano probably more than the other two. But there's just a couple reminders on our metric prefixes. And then the other thing to remember is, since we haven't done this in a while, is the thought, is there a lot of nanometers in a meter, or is it the other way around? The nanometer is very small, and so there should be a lot of nanometers in a meter. So I can write 10 to the 9 nanometer in 1 meter and do the conversion that way. Or I can use the fact that the nanometer is very small. It's a 10 to the minus 9 meter. So either one of those two calculations will work. The one that won't work, of course, is 10 to the 9 meters per nanometer. That's wrong. So we don't want to make this 10 to the plus 9. If we have this plus 9, that's not going to work. So we got to have 10 to the minus 9 meters per nanometer, or we need to flip it to 1 meter contains 10 to the 9 nanometers. And again, we haven't done that calculation in a while, so I just wanted to make sure to point that out. And so if you want to do this with me, that's fine. So 2.9979 e to the 8 divide by 725. Now, if we put it this way, I can type 725 e minus 9. And my calculator, that's 725 times 10 to the minus 9. So I'm doing 2.9979 e8 divided by 725 e minus 9. There's other ways to put this in your calculator too. So that's 4.14 times 10 to the 14 inverse seconds. Seems silly, but if it's been a while since you've used scientific notation, for a problem like this, it's easy to kind of look at this and say, how do I put this into a calculator? Either do 725 e minus 9, or do 725 within parentheses and then times 10 caret minus 9 is another way to put it in. So there's so many different ways to not mess up this calculation. And so that's how we can calculate the frequency for a photon in this region. Now we know this from what we saw in the previous slide, that this is a visible region photon. So this photon's in the visible region, probably in that red, orange region, which again, I don't know if I would necessarily memorize the specific cutoffs of the colors of the rainbow, but just the blue violet's on the 400 side, the red orange is on that 750 side. So now another topic we want to get into in this chapter is how energy is quantized, so that certain processes are going to take a certain amount of energy in order to take place. Now I think this is good, because if this weren't the case, then how could you ever have like a stable molecule? How could anything ever be stable for a certain lifetime and not just decay spontaneously? It's through certain events requiring a certain amount of energy to take place. And so we see this with like black body radiation. You can think of like flames of a stove. You can think of how like a yellowish part of the flame is cooler than the blue part of the flame. Well, why would that be the case? Well, you've already kind of seen it. It's because the color is associated with temperature, that as you look at the color of the flame, it's telling you something about the temperature of the flame. And so the color of a flame is related to its temperature. Glowing objects, like a white glowing stove burner, is giving off a lot of heat as it's giving energy off. You can think of the color being associated with heat. So we can think colors of flames or of objects have been associated with their heat or their temperature. And so then the photoelectric effect is that when we take light particles and then shine them onto objects like, say, metals, that we can have events take place like ionization. You can ionize a metal where electrons are given off by ionization. So you have the metal absorbing light, which, let's just write metal plus light. And then this could give you the metal cation plus an electron, where the electrons fly off the surface of the metal. So you kind of take maybe a laser or some light source, shine it out of metal, and then it can cause electrons to be ejected from the surface of the metal. Now, not just any photon of light, though, or any wavelength of light is capable of having this type of reaction take place. The light particles have to carry enough energy, or this experiment really is the one that allowed us to determine that light's carrying energy, and that when light has a certain wavelength or smaller, or when light has a certain frequency or greater, it allowed the photons of light to be ejected. And so the ejection of light requires light to be of a certain wavelength. So light of certain wavelengths and frequencies, and what was found is that the wavelengths have to be some lower value. You have to find like a threshold wavelength, that threshold wavelength or lower, and then since you can calculate what frequency that wavelength's associated with, it's going to be that frequency or higher. So you find like the certain wavelength that just begins to allow the electrons to be ejected. If you go to lower wavelengths, that's greater energy. Electrons can be ejected by the metal. And if you go to higher frequency, then photons can be ejected as well. This led to the discovery of the photon energy, that the energy could be calculated for a single photon by the equation E is equal to h nu, where h is Planck's constant. I think it's given on the very next slide, but h is Planck's constant. The numerical value is 6.626, and you could look it up more precisely, so that's why the ... I write, and then times 10 to the minus 34 joules times seconds. And just interestingly to point out, it's joules times seconds, not joules per second. And so the units here are the units of joules, and then the units of seconds. And so this allows us to calculate the energy associated with a single photon. It kind of gives us the relationship of, we can think of single particles in their masses, like in the periodic table. We can then think of light as being indivisible to to one single photon, where we can calculate the energy of a single photon by taking Planck's constant and then times the frequency of the light in inverse seconds. So h, joules times seconds, frequency inverse seconds, gives us the energy of the light in joules. This gives us the energy per a single photon, for just one photon of the light, the most, or the least indivisible portion of light that you can have is a single photon. And then you can also just use the conversion we had before, that nu is equal to c over lambda, and then sub that in for frequency, so you can calculate your photon energy, which is h nu. You can sub in hc over lambda. And what this allows us to see, just converting wavelength, you're just converting nu into c over lambda, so that you can see that if you go to a higher frequency, the photon energy goes to a higher energy. And then if you go to a lower wavelength, then you go to a higher photon energy. So as the photon's wavelength decreases, its frequency therefore has to increase, that those events lead to a higher photon energy. So if if we go back to the 725 nanometer photon, so if we make that wavelength lower, where do we go? We go towards that 400. We go towards that blue-violet portion where we know that was a higher energy from where we kind of started the topic. So I go into a lower wavelength, we go to a higher energy. So the idea would be, like, if you know a 725 nanometer photon, let's say you shine it on a piece of metal and it doesn't lead any electrons to falling off the metal, then you know that that is not yet at the ionization threshold of the metal. You would say, well, go to a lower wavelength. You would say, try a 600 nanometer photon. If that doesn't work, try a 500 nanometer photon. But you're gonna reach a point, let's say, in a given metal will have a characteristic ionization potential, but the idea is it takes a certain amount of energy per metal to cause that electron to be ejected, because each metal has an ionization energy, an energy that has to be overcome in order for the electron to be ejected by the metal. And so let's say you hit it at 400 nanometers. 400 nanometer photon causes a stream of electrons to be ejected by a metal, and if you keep going lower, it's even more energy. You continue to have electrons be ejected. You could also say at 725 nanometers, if you increase the frequency, that would work too, because increasing the frequency takes that wavelength lower. So it takes it to a lower wavelength. So increasing the frequency would lead to a lower wavelength, which would lead to a higher photon energy. And so this is described here, or kind of the summary of what I was just saying in the previous slide in terms of handwriting that's not mine. So the photoelectric effect is that metals can release electrons when they're shined with light of some minimum frequency. And then we go to higher frequency, and that causes them to have more electrons ejected. And each metal ends up having a characteristic ionization energy. But the idea, I think, is that there is some threshold energy that has to be overcome. And like most reactions are going to have that idea that it's not any amount of energy that causes the reaction to take place, but overcoming that threshold. And so then this is what allowed Einstein to calculate that the energy of a single photon, so this is the energy of a photon, is equal to E is equal to h nu, or as we showed earlier, hc over lambda, where h is Planck's constant, rounded to 4 sig fig, 6.26 times 10 to the minus 34 joules times seconds. And so now this just allows us to sort of think at almost like the idea being the molecular level, that for a single metal atom undergoing a single event takes a single photon of light. So it's kind of just thinking that one metal or one molecule, the least indivisible form of matter, can interact with one single photon. So a metal atom plus a photon, as long as the photon carries enough energy, can lead to a metal ion, plus the electron that's freed. And now this topic is like really less about the metal. Like it may seem like, okay, we're gonna get into like ionization energies and different metals and look at them, but it really is less about the metal, but more about just like the discovery of this equation and the relationship that energy can be calculated for a single photon, because the single photon is like the least, it's sort of that atom level. It's the one photon interacting with one molecule, and we can calculate the energies of the event that the atom has to undergo and relate it to the energy that the light had to contain to cause that event to take place. And so this is also what leads to the wave-particle duality of light, where we know light's described as being a wave, but here we're thinking almost like throwing a light at a metal where light doesn't contain any mass, but it's like we're taking a massless particle and causing a reaction to take place with it, and so that gives us that wave-particle duality of light. So we can calculate or solve a problem like this one here that says, well, if a metal has a characteristic ionization energy of 425 kJs per mole, then what wavelengths of light, if shined onto the metal, are capable of ejecting electrons? So the idea here would be, we'd have to think per one metal. Like, what's the ionization energy of one metal atom? Because the photons can interact with one of those atoms at a time. And so what we might just want to say is, well, what's the ionization energy of just one metal atom? Well, if it's 425 kJs per mole, I just need to do the 1 mole of that metal. That's called a metal M. So 425 kJs per mole of M. If I take 1 mole of M and just use Avogadro's number, Let's convert it to joules too. Why? Well, because I'm going to use Planck's constant later. So I'm going to use joules times seconds in a calculation in a minute. So why don't I go ahead and get this over to joules? So a kJ is 1,000 joules. So if it takes 425 kilojoules per mole to break the bonds of the metal, just think of how much energy it takes to break one metal's attraction to its electron. So the ionization energy for one metal atom would be 425 divided by Avogadro's number, and then times 1,000. I get 7.06. Let me carry an extra digit. 7.057 times 10 to the minus 19 joules. It's a really small number, of course. So we're trying to calculate the ionization energy of just one of the metal atoms. And now the idea here is that our photon can interact with one atom, one photon at a time. So one photon can interact with one atom. So we're going to say that or just try to understand that the photon energy has to be equal to or greater than 7.057 times 10 to the minus 19 joules. So our photon has to carry at least this much energy or greater, then it can cause that electron to break its attraction to the nucleus. If we have less energy than this, there's not enough energy to break the attraction. And so our photon energy, the book always says E is equal to h nu. I like E photon. Just remember that's the energy of one photon. So the energy of a photon, which is hc over lambda, that this energy has to be greater than or equal to 7.057 times 10 to the minus 19 joules. Now, do you see that if I think of the energy had to be greater than this amount, and if I do my arithmetic, and if I remember how to do greater than or less than calculations, if I multiply lambda onto both sides, then I'd have lambda over here, and I keep the greater than sign pointing in the same direction. Do you see how my wavelength has to be less than or equal to hc divided by 7.057 times 10 to the minus 19 joules? And I knew it should be some threshold wavelength or lower too, because that would be that wavelength or greater energy going to a lower wavelength. So I can calculate what wavelength I need to go to and also get the right directionality mathematically. I can think about it too. I can just think about how when I calculate the wavelength precisely associated with this energy, I want to be at that wavelength or lower to go to a greater energy. Okay, so let's sub in here H and C. So we want our wavelength to be less than or equal to 6.626 times 10 to the minus 34 times the speed of light, 2.998 times 10 to the 8 meters per second. You can go 997, whatever. As long as we carry enough digits that we're not rounding based on our digits here. We have 3 digits on our energy problem. Unit-wise, our per second and the meters per second are canceling into the joules times seconds. So again, remember joules times seconds helps us know that we're multiplying by the speed of light here, and we're dividing by 7.057 times 10 to the minus 19 joules. Joules cancels. So we're calculating our wavelength here in units of meters. Now I get my wavelength has to be less than or equal to 2.81 times 10 to the minus 7 meters. Just to make sure, I'm going to switch my calculator to scientific mode. Yeah, 2.81 times 10 to the minus 7 meters. And then I'm going to convert to nanometers, because we tend to think of light if this is going to be in the UV region, but we're probably going to most likely convert most wavelengths for light in this region to the nanometer range. And so 1 meter, 10 to the 9 nanometers. So a lot of nanometers in the meter. That gives me 281 nanometers. So for 425 kJs per mole, to break the bond for a single atom would take 7.057 times 10 to the minus 19 joules. That would be associated with the energy contained by a 281 nanometer photon. This is in the UV range. I'm just interpreting that because I know this is close to 400, but lower wavelength. So this is the higher energy side of the visible, so that would be the UV range. And then I know that I want to go to this wavelength or lower. So I want to be at 281 nanometers or lower here to cause electrons to be ejected by this metal. Okay, now in a way, I hope this is just proving the concept that like light contains energy, how much, calculated based off of E equal hc over lambda, how high is the ionization energy, relate that to a single atom, and then for a single atom, single photon, just calculate the wavelength associated with that transition and think about how we want to go to lower wavelengths to go to greater energy. Now, where we go from here is to try to then understand, okay, if light contains energy, we can calculate like the energy of a photon, we can calculate how that photon can cause events like ionization to take place. We then kind of get into, well, what is it that causes light? Like when you think of a light bulb in a room, what is it that allows a light bulb to light up? Well, depending on the type of light bulb that you're using, you have high voltage energy absorbed by some type of gas or some type of metal, like a tungsten filament, the old style light bulb. The energy that's absorbed by the metal heats it up, and then it goes to some high energy state that then gives light off as it returns back to a low energy state. So most light that we see involves usually from some high voltage source creating some sort of a hot state, and then when that hot state returns back to the cool state, or the lower energy state, light's given off. And so that's the basic idea of most light sources, is you have some way of creating some excited energy levels that then coalesce down to some lower energy levels, and then the energy difference, and we start to think of this as undergoing, imagine one tungsten atom in a strip of tungsten. You can remember the old light bulbs, maybe you guys can, before they change like the light bulb types. But if you just have a light bulb with a piece of metal in it, the metal would absorb energy per each of the metals going to some hot state, and each of the metals, when it returns to the low state, gives the light off that you see with the light bulb. Now, when we do this with a hydrogen source, so imagine, well, let's start with the visible like light source from like a flashlight. With the flashlight, you're gonna get, or like the room lights, you get a kind of a rainbow. If you take the light, pass it through a slit, pass it through a prism to allow the different wavelengths to separate, you kind of see most wavelengths there with our visible sort of light coming from a visible light source. But now, what if we change that light source to something like a hydrogen lamp? So what a hydrogen lamp is just where we pass a high voltage through a tube that just has hydrogen gas in it. So we pass a high voltage through a hydrogen tube with hydrogen gas in it. What the high voltage does is it takes the H atoms, breaks the bond, some of them, just a few of them at a time, into single H atoms, and it creates these hot H atoms. And so we have hot hydrogen that has to then coalesce into cool hydrogen. And if you think of this just like the photoelectric effect, if you think of one H atom that's in a high energy state returning to a low energy H atom, then you can imagine light's given off by the events of that process. And the interesting thing with hydrogen being a single atom with one electron, so each H atom has one electron, that you get a well kind of defined spectrum. I don't know how well you can see the actual spectrum. Let me zoom in here so you can actually see that there are 4 distinct lines or transitions that you can see in the visible spectrum for hydrogen. So you take your hydrogen lamp, you have your light source, you take the light source, pass it through a slit so you can take a narrow portion of the light, pass that light through a prism, separate the wavelengths, and instead of getting a rainbow, we get 4 distinct transitions. And then the transitions here are specifically looking in the visible region. So there could be other transitions that hydrogen undergoes that just don't fall into the visible spectrum. And so a question kind of, that arose was, well, what leads to these transitions to having taken place? And so it led, scientists to develop some equations. Balmer found an empirical relationship was if you invert those wavelengths, you can set them equal to what he called, or what was called the Rydberg constant, and then times 1 over n1 squared divided by 1 over n2 squared, where these values here were whole numbers. and then one of them was 2, so the N1s turned out to be 2 for all of them, and then the N2s were either 3, 4, 5, or 6. And whether it was 3 or 4 or 5 or 6 gave you the proper wavelengths, so you can calculate the wavelengths on the previous page. I'm less interested in how that equation works. I'm more interested in why the equation works. And so there's a later equation that we're going to look at. I think it's on the very next slide, where Niels Bohr is going to try to take a look and try to come up with a little bit of a better explanation for why we were seeing these 4 specific transitions and what these n values have to do with. And so what the Bohr model attempted to do was it attempted to say, well, let's think of these n values as relating to the energy levels of our hydrogen atom, where n equals 1 is just the lowest energy level, and then the N2 is a higher energy state, and 3 even higher. So these are our hot atoms, or hot states, if you will, the higher energy states. And then this is our ground state. So the lowest possible state is that n equals 1 state. And so the idea was that the high voltage source is creating excited atoms that then were coalescing down to their ground state. So if you imagine the transitions from 6 to 2, 5 to 2, 4 to 2, 3 to 2, that those are the H atoms returning to the n equals 2 energy level. And the reason why you see these in the visible region just turns out that these photons here happen to fall into the UV region. You have all of these events taking place. If you have an H atom created, let's say in the n equals 6 level, some of them will be going to 5, some to 4, some to 3, some to 2, some to all the way to 1. So you'll have all these different transitions taking place. It's just the states or the cases where the atoms are returning all the way to the n equals 1 level. These are really high energy photons. These are in the UV region. So those take place, they just don't occur in the visible region. So hydrogen can undergo transitions from 6 to 1, 5 to 1, 4 to 1, et cetera. And those transitions would be visible if we could see transitions in the ultraviolet region. So if we extended our experiment to be able to look at UV photons, if we did this in a vacuum system and had the ability to see those transitions, we could see those too. And so then if we could look at the spectral region in the infrared region, we could see these transitions here too. So we have IR region photons being the ones that are going from 6 to 3, 5 to 3, 4 to 3. And you can also have hydrogen in higher states. You can have hydrogen in n equals 7, n equals 8, n equals 9. The H atom can be excited in upwards to n equals 40 to 50. If we have time, I'll share a couple experiments I used to do where we would actually have hydrogen absorb up into what we would call Rydberg states, in these high energy states where the electrons is very loosely still attached to the nucleus of the H atom. So then the idea is that what we're doing here is we're just taking the electron in n equals 1 and pushing it further away from the nucleus in n equals 2, pushing it even further away from the nucleus in n equals 3. So the idea is as you go from n1 to 2 to 3 to 4, you're just pushing the electron further and further away from the nucleus. And so the reason why then these only take on whole number values, no one knew. So why did n have to be 1 or 2 or 3 and not 2.5? Why does it have to be whole number values? Well, nobody really quite knew until we get into wave mechanics. We get into the Schrodinger equation, which we'll briefly look at, not really do much mathematically with. But the reason why these take on whole number values, even the reason why n can't be 0 isn't explained. It's just more like an observation. So slight bit of an observation, a little bit of an explanation is just the H atom's changing its radius of orbit around the atom. And then you have an equation that you can use that Bohr took it past the Rydberg constant. He then multiplied it by hc, so you could calculate the energy of the atom, where the energy is minus 2.179 times 10 to the minus 18 joules. So the units here are joules times the 1 over the n value, and then you can calculate a delta E. You can take the E final minus the E initial. So you could calculate the energy of your hot atom, the energy of your cool atom, the energy lost by the atom. Where does it go? It goes to the photon. This becomes like a system surrounding problem, where the H atom's your system, losing energy, the energy lost by the atoms given to a photon. So we'll pick up from here next time, where we'll look at the atoms in the high states can lose energy, create photons, give photons off, and we can take H atoms in a low state and have them absorb into the high state by the absorption of energy. Okay, so we'll pick up from the Bohr model on whatever day is next, Friday. Have a great day, guys.